Okay, only a few more videos left, guys, as we wind down the school year. Section 9.7, statistics and data, and there's actually two parts to this. Obviously, there's two sections, but this first section, 9.7, is going to be more of the graphical approach to stats, and then 9.8 is going to be more of the algebraic, the numerical stuff for stats. So what we're trying to get accomplished here is we want to be able to distinguish between categorical and quantitative variables and use various kinds of graphs to display data. Now, those graphs can include stem and leaf plots, they can involve histograms, they could be box plots. In other words, stuff that you guys probably did back in middle school being honors kids. So just kind of refresh your memory on some of this stuff. Okay, so the first thing we're going to talk about are stem plots. Now, that stem plot is the same as stem and leaf plot, okay? You can see the definition there. The stem consists of the initial digit or digits, and the leaf, which is the last digit. So in this table, okay, this is a table of the percentage of each state's population that was 65 or older in the 2000 census, and they want us to make a stem plot. Well, if you look at all the numbers, they're all decimals. So what we're going to do is the stem, okay, is going to be the number or numbers before the decimal point, and the number after the decimal point will be the leaf. So if you take a look at all the numbers, okay, the lowest number would be 5, and the biggest number, it would appear to be 17, it looks like. So we're going to do our stem 5, 6, 7, 8, 9, 10, 11. I'm going to run out of room. You guys can finish this, okay, on your. So when you do these, okay, you can see how the stem and leaf plot is made. Okay, I'm going to expect you guys to finish that. I'm going to be looking for it. Okay, that's going to be part of whether you finish the notes or not. So this should remind you how to do a stem and leaf plot. Now, same thing over here, okay, except this time we're going to make something called a split stem plot. So we have our stem and leaf plot, and what we've done, and by the way, what we want to do here is round to the nearest $100. Okay, if you read the problem, it's the per capita federal aid to state and local governments for the top 15 states in that category. Okay, they want a stem plot that provides a good visualization of the data. Now, what that means is that what I'm going to take, so for example, Alabama is $3,713. If I round to the nearest $100, that's $3,700. Wyoming is $2,800. Now, North Dakota is $1,900 automatically. ME is Maine, not me. Maine, that's $1,800. Okay, Michigan is $1,700. So you round all those to the nearest 100. Now, what I'm going to do is a split stem plot means I take two stems and I take a stem. Excuse me. I take one stem and I split it into two separate stems. Now, the first number is the same, 1 and 1, but the first one is only going to deal with leaves from 0 to 4. The second one is going to deal with leaves from 5 through 9. So as you can see, there are only, in the table, there's only two values that are between $1,000 and $1,400, 4 and 4. Now, there are several that are between $1,500 and $1,900, okay? Now, again, if they repeat, you have to repeat. You have to write them all. So if they repeat, write it. Okay, and again, I'm going to expect you to finish that. Okay, I will be looking for that when I check your notes. Oh, we got to go back. It says, what is the average of the 15 numbers? Okay, so now what they want you to do is find the average. Well, you guys know how to find the average. Okay, you know how to find the average. Add all, now don't do the rounded ones, just do the actual numbers. So find your average. Whoops. Okay, your average is the sum of the 15 numbers divided by 15. Now, you get about 1,967. Okay, That's the average, the actual average. Now, it says, why is the stem plot a better summary of the average of the data than the average? Okay, well, because there are 11 numbers, okay, that are lower than the average. Okay, so all these right here, all those numbers are below the average. Okay. Now, what that means is, so you have 11 numbers lower than the average. Okay. Now, where is the so once you finish the stem and leaf plot, once you complete that, okay, where is the distribution kind of tightly packed around? Okay, well, the distribution is tightly packed around what? Well, it looks right here, you've got a lot of numbers right in here, right? So it's tightly packed around $1,800, right? Everything seems to be packed in tight there. Now, obviously, an outlier is a number that doesn't really fit in with the rest of the data. Well, Alabama is an outlier because Alabama's total is pretty significantly bigger than everyone else. So it kind of stands out by itself. So that's one way to kind of analyze one of these stem plots, okay? All right, cheaters. Mark McGwire and Barry Bonds entered the major leagues in 1986 and had overlapping careers until 2001, the year that McGwire retired. During that period, they averaged 36.44 and 35.44 home runs per year, respectively. Compare their annual home run totals with a back-to-back stem plot. Can you tell which player was more consistent as a home run hitter? Well, back-to-back means you're making two stem plots, but you're putting them in the same plot. So, 0 means single-digit seasons. Barry Bonds did not have a single-digit season. McGwire had 3. He had 3 homers, 9 homers, 9 homers. So 3, 9, 9. Now I go to the teens. Okay, so I go down the list. McGwire, his first teen home run. Well, he never had a teen home run season. Okay, Bonds had 2. Whoops, 16 and 19. Okay, 16 and 19. Early in his career. For those of you that may not know, Barry Bonds started his career with the Pittsburgh Pirates and was a phenomenal baseball player and did a lot of great things, but Pittsburgh wasn't for him, so he went to San Francisco where he spent the rest of his career. McGwire started his career with the Oakland A's, was an unbelievable first baseman. Him and Jose Canseco were nicknamed the Bash Brothers because they were both monstrous human beings that hit really far home runs. They actually won a World Series together. And then McGwire left and went to the St. Louis Cardinals where he finished his career. But they both cheated. So, anywho, history lesson over. Now let's go to the 2 stem. Okay, so now we're looking for home runs in the 20s. Okay, so McGwire's got a 2. He's got a 9. Okay. Bonds has 24, 25. 25. Okay, that's it. So, again, you got to put them in order. So 4, 5, 5. 30s. Okay, McGwire's got a bunch. 32, 33, 39, 39, 32. So 2's the smallest number, so we'll put 2 first. Actually, it goes twice because it shows up twice, and then a 33, and then 2 39s. Okay. Bonds is going to have a bunch of 30 home run seasons. So let's see, 33, 34, 37, 33, 37, 34. So let's see, 3 is the smallest, that shows up twice. 34 shows up twice. And 37 shows up twice. Okay. Now let's go to the 40 home runs. So 49, this is for McGwire, 42, and that's it. So 9, 2. Bonds, 40 home runs, 46, 42, 40, 49. So 40 is the smallest. And then we go to 42. Let's see, 46 and 49. Okay. McGwire had two 50 home run seasons and a 60 home run season. Bonds had the 73 home run season. Okay. He had the 70 home run season. So, there's your back-to-back stem plot. Can you tell which player was more consistent as a home run hitter? Well, McGwire's are more tightly packed together. Okay. He had anywhere from 20, the majority of his career was from 20 to 60 home run, 20 to 65 home runs. Okay. Bonds was more of 16 to 49. Okay. So we would say that McGwire is more consistent. Now, another reason why is look at Bonds. 73 home runs is an outlier because he didn't hit any more than 50 ever in his career. And then one season he hit 73. Okay? So that's an outlier. That doesn't really fit in with this group of home runs. That's why McGwire's a little bit more consistent. Okay. Now, last one, it says make a histogram. Okay, so the first thing we want to do on the histogram is, these are his annual totals. So what we want to do is we want to make a frequency table first. Okay, and so what I've done is I've grouped it up by every 5 home runs. So from 10 to 14, 15 to 19, 20 to 24, and so on. Now the frequency is how many times does that happen? So you would have to go back to here and go, okay, how many times did he hit 10 to 14 home runs? Count them up. So he did that 3 times. I'll save you the time. Okay, I already worked this out. By the way, you want to talk about consistency. Hank Aaron had it. Oops. It's one of the greatest of all time. Okay, so the total is 23 because Aaron played 23 seasons. Okay. Now, you can make a histogram on your calculator, which I don't know if you know how to do that or not, but I'm going to take you through the process. All right. So you're going to do second, y equals. Then you're going to make sure plot 1 is on, and then you're going to choose the histogram. Put the HR totals in L1. So what that means is that you've got to put each individual home run total in L1. So you're going to have 23 values in L1. Then in your window, you want the X min to be 0 because obviously he didn't hit, well, first of all, he didn't hit 0 home runs. Second of all, you can't hit a negative number of home runs. X max we want to put at 55. His greatest home run, he never hit more than 49 home runs in a season. So you always want to make your X max a little bit bigger. Okay. Your X scale is 5 because that's the scale we use in the frequency table. Your Y min is -1 just so we can clearly see the histogram. And then your Y max is 7. Okay, because the frequency is, the highest frequency is 6, so you go a little bit bigger than that. Okay, and then you graph it, and then you'll see your histogram. Okay, so when you're doing a histogram, do a frequency table, and then follow those directions on the calculator. And that's it for 9-7.